Hi, everyone. This is your first note section, and we're going to talk about real numbers and variables. It'll be vocabulary heavy, and a lot of terminology will be introduced here. And that's okay because as you guys are starting into your upper level math classes, you need to start getting better at using some of this vocabulary. So it's going to be new, and that's going to be okay. I have to view the slideshow like this because whenever I presented it, it was cutting off the bottom. So we're first going to start about just talking about the number line. Okay, you've had lots of experience with the number line for a very long time. And the first thing you should do when you look at a number line is you should figure out what the scale is going on here. So 0 is a good place to start, and then you're looking at 1 is all the way over here, 0.5 is here. So it looks like we're counting by 0.1, 0.2, 0.3, 0.4, 0.5. Looks like we're counting by 0.1s. So when you're figuring out what point is represented by these decimals that they're asking. Look, there's not a question mark. -1/5. If you want, you can change these to a decimal. Now, -1/5 is something you should know, but just a reminder of how your calculator works. You can put -1, divide by 5, enter, and it will change it to a decimal for you, -0.2. So this is the same thing as -0.2. Now, where is -0.2 on the number line? Well, A or B are pretty close, so you might be a little confused here. But if we're counting by 0.1s, A is where -0.2 is. Now, how about 9/5? Hopefully you know that would be the same as 1 4/5 or 1.8. But if you did not remember that, your technology can help you, and you can take 9 divided by 5, and you're at 1.8. So which one of these guys is at 1.8? Well, here's 1.5. We're talking about F is at 1.8. And then the last thing you're looking at is -0.1525. Okay, so here's -0.1. So this would be the B one because A was already accounted for, and that's looking at the number line. Okay, that's complete review, and it might seem like baby stuff. This can also be a little bit confusing. Which one of these best represents this guy? Well, clearly it's we're going by ones this time. It looks pretty close to -4. Now, it's not -4.44 because that would be beyond that. Pi as a decimal approximations will help you here, is about -3.14, -1, -2, -3. Well, that's reasonable, but I would think that would be closer to here. -11/3 as a decimal, if you need to get a little bit of help, -11/3. You're looking at -3.6. Repeating, that seems even more reasonable. -1, -2, -3, -4. It's a little bit further than that. That seems pretty reasonable. And how about negative square root of 17? Well, negative square root will be second x squared, 17, -4.1, and that's too far. So our best bet will be -11/3. Okay, so that's a little bit of number line fun. Now we're going to talk about different types of numbers. Okay, and the first types of numbers we're going to talk about is pretty much the biggest set that you are aware of at this point, and this is called the real numbers. Real numbers have a symbol. It's this double bar R. And basically, if you can graph something on a number line, it's a real number. And so far in your life, this is the biggest set. This is pretty much all you have experience with. So when you go back to this page, all of these are real numbers. Even though negative pi has decimals that go on forever, I'm stuttering, excuse me. It can be graphed on the number line. You can put it on here. So any number that can be on the number line is called a real number. Now, inside the real numbers are different subsets. So we call these the real number sets. So the real numbers are all of these guys. And then what you have here, and this guy will be the smallest set, and it's the natural numbers. The natural numbers symbol is a double N bar type like that. And it is the numbers that come up naturally when you're counting 1, 2, 3, 4. Okay, and you go on forever. It makes sense to most people. If you ask a small child about the number 0, That is kind of confusing. If you have a basket and you say, how many balls are in this basket? And there's no balls in there, that is very confusing to the kid because they don't know how to count it. It's not natural. Now, the whole number is a little bit bigger than the natural numbers. It actually just has one more element. This is a double bar W. I don't even remember where it goes. Maybe there. I don't know. It might go maybe there. I don't know. It's just double bar somewhere. And it starts with the number with a hole in it. A hole in it, 0. So the whole numbers start with 0, and then it is the rest of the natural numbers. Now, the integers are your positive and negative whole numbers. So this symbol is actually really surprising. It's a Z. Okay, so then you have the numbers that go forever, and then you have -3, -2, -1, then 0, 1, 2, 3. So you have the whole numbers, and then you have their negative friends. And then we have rational, which has the root ratio, and these are numbers that can be, its symbol is actually a Q with the double bar in it, and Q stands for quotient, which means divide, because these can all be written as a ratio of two integers. So 5 is rational because it can be written as 5/1. 3/2 is rational. 1.5 is also rational because you can write it as 3/2. If you have 0.6 repeating bar, that is also rational because it can be written as 2/3. Basically, any decimal that is repeating or that terminates, which ends, is rational. Okay, and then irrational, it means not rational. It is a double bar Q with a bar on top of it. That means the complement of rational. So it's the rest of the numbers that are not rational. These cannot be written as a ratio. And these numbers are the special ones. So you're talking about pi. The decimals do not repeat. That's a really bad pi. You're probably really upset by that. There's a special number called E that we'll learn about later this year. Square root of 2, the decimals do not repeat. Square root of 3. Now, square root of 4 is not irrational because square root of 4 is 2, so that would be rational. So you have to be a little bit careful. There are some other decimals like 1.01, 0.001, 0.0001, 0.0001. If we repeat that forever, some of you might say, well, that's a decimal that repeats. No, there's a pattern that repeats, but this cannot be written as a decimal because the entire numbers don't repeat. Okay, so if you want to look at a little chart organizing these guys, you basically have all of your real numbers, and then you have your rational numbers that can be written as a fraction, and then those irrational numbers that cannot. Those make everything up. So this is the square root of 2 and the pi and everything. The natural numbers are the smallest set, then the whole, integers, and all of those are rational. Now, it's kind of funny how much bigger that whole circle is than the natural because the only extra element there is 0, but that's just the way they keep track of it. So what is a fact you can tell me based on this chart? I'm talking about things like this. All natural numbers are integers. Okay? You could say all whole numbers are rational. You could say not all whole numbers are natural. You can say things like that. So when I'm asking you about a fact based on this chart, I'm asking you about the all statements. Okay, so let's classify these numbers. Negative 2.22. So let's go back to our chart. It's definitely not natural because it's not a regular counting number or a whole number or an integer. So then you're really left with just rational numbers and irrational numbers, and it's definitely going to be real. So the question is, can you write it as a fraction? Because this decimal does end, you can. So it's a real number, and it can be written as a fraction. It would be negative 2 and 22 over 100. And you could write it as an improper fraction from there. Okay, how about 5? If you look at the number 5, is it natural? Yes, it's a counting number, which makes it a whole number, an integer, rational, and real. So it is all of those. Natural is the most descriptive, then whole, then integer, rational, real. Okay, this idea of density. Density is really kind of a cool idea because it's thinking about zooming in so incredibly far. So if a number set is dense, that means there's always a number in between two numbers. So the example that I'm going to give you is this rational numbers. So if you talk about 3 and 4, definitely there are a bunch of numbers that could be written as a fraction between 3 and 4. Okay, so like 3.2, that can be written as a fraction, and 3.3. Now there's also numbers that can be written in between those, 3.22 and 3.23. There's numbers that can be written in between those, and it can go on forever because the rational numbers are dense. Now, irrational numbers are the same way, and that's because if you think about like the square root, or you can think about pi, because pi, and you could do like pi plus 1, and then you could do pi, and you could do something like pi plus 0.1. Like you can keep adding numbers, and it would still be irrational. The same thing with square roots, the square root of 2 and the square root of 3. You could put the square root of 2.1 in there, and those numbers would be dense as well. Now, integers, on the other hand, are not dense because when you have 1 and 2, is there a number that's an integer that can be written in between there? And the answer is no. Okay, now ordering these things on a number line, you will want to use approximations to put those from least to greatest. So I would get my calculator out and I would take the square root of 22. Oop, too many. It's a little touchy. All right, 4.69. Okay, 4.75 I can compare with. I like to think about money. This guy here, 2.85 e to the 1/2. There is a button called e on your calculator. 2.85, it's right here. If you hit second natural log, there's e, it's a number, to the 0.5 or 1/2, 4.698. Okay, now this one was 4.690 if I remember. This one is 4.698. Then I have 3 pi over 2. So 3 second caret there is your pi button. 3 pi divided by 2 is 4.71. And then you have 380 over 79. $4.81. Okay, so if we're going to go least to greatest, if you think about money, that will help you. It looks like the square root of 22 is the smallest. And then we'll go to 2.85 e to the 1/2. Now we're going to the 70 cents. We're going to do 3 pi over 2, 4.75, and then the 4.81, which is 380 over 79. So you'll want to use decimal approximations to help you with that. All right, we're going to talk about closure property on the next video. This one's getting a little long, so we're going to take a little break.